Welcome everyone. This is our first video related to the topic of tree, and in this I am going to talk about the basic terminologies associated with tree. In case if you are new to the channel, you should subscribe it because it will be helpful for you. Now let us talk about it. What is the definition of a tree? A tree is a connected undirected graph with no simple circuit. So 2 points I am highlighting. It is connected, and second one is that it should have no simple circuit. So here are few examples. If you look at the first one, this is a tree. Why it is a tree? Because clearly it is connected and it has no simple circuit in it. When I say it is connected means, I hope you remember the definition of a connected graph, that between any two vertices there is a simple path, right? So there is a simple path between any two vertices. So you can move from A to D, you can move from B to C, you can move from B to F. So this is a connected graph. If you talk about this example, this is also a tree because this is connected and there is no simple circuit in it. This is not a tree. The reason is that it is connected, but the problem is that it has a circuit because you can move from A to B. So if you move from A to B and then you move to E and then E to D and then D to A, so you realize that you are completing a circuit. I repeat it: A to B, B to E, E to D and D to A. So since it has a circuit, it is not a tree. And this graph is not a tree because this is not even connected. You can't move from A to D. There is no simple path between A to D. So this is not a tree. There is a very important theorem related to tree, and it is known as an undirected graph is a tree if and only if there is a unique simple path between any two of its vertices. And it means what? That if I am saying that an undirected graph is tree, then we can conclude that there is a unique simple path between any two of its vertices. Or if I say that there is a unique simple path between any two of its vertices, then we can conclude that this is a tree, right? So this is a very important result, and I hope you can clearly see from these two examples that in this, if you take any two vertices, there is a unique simple path between those two vertices. For example, if I take B and E, so there is a unique simple path because we can move from B to C, C to F and F to E, right? So this is the theorem which you should keep in mind. Next thing that we are going to talk about is rooted tree. And in rooted tree, what we do, we designate one of the vertex as root. So to understand this, let us draw its rooted tree representation, and while drawing it, I am going to consider two different vertices as root, one as A and another as C. So if I consider the vertex A as the root, all other edges will be directed away from the root. So I have a vertex B here, and this is an edge which is directed away from A. So this is how it should be drawn. And then we have C, right? We have C, and we also have D here. So A is adjacent to these three vertices. Now if you look at B here, so B has two vertices, and I am drawing the edges which are directed away from B. So this is F and this is G. C has one vertex, so I am going to join this edge like this, and the purpose of drawing this, that I am drawing the edge in such a way that it is directed away from it. That is what the example suggests, or the definition suggests, that every edge is directed away from the root. So the root is A, and we are drawing the vertices in such a way that the edges are directed away from the root. And finally we have D, right? So this is the rooted tree representation of this graph. If I suppose change the root and suppose I take C as the root, okay, so if I take C as the root, there are two vertices which are adjacent to C, and one of them is A and another is E. See, we are going to use different terminology like children, ancestor, descendant, all this, but first understand it. Next slide we will be talking about those details. So C has two adjacent vertices, that is A and E. Now if I look at A has two adjacent vertices, that is B and D. So I am going to draw it in such a way that it is directed away from the root. So here I am drawing it and I am calling this vertex as B and this vertex as D. Sorry, D, not G. Give me a moment. Let me delete this and write it as D. Okay. So you can see that this vertex A has two adjacent vertices, that is B and D. Now B further has two adjacent vertices which are like A is already joined, so those which are like F and G. So I am going to write it here F, and this vertex I am going to write as G. So this kind of representation for a tree is the rooted tree representation, and here I have considered C as the root. So here this C is the root and here the root is A. So A is the root, and the way it has been drawn, the idea is that all other edges I am drawing so that it looks like it is directing away from or directed away from the root, right? So it is like we are moving away from the root. Okay. So now let us understand some of the important terminology, and this is important because most of the time in exams they ask questions related to this. I would suggest you to pause the video and first note down all this terminology, or if you want to take a screenshot, whatever is better for you, you can do that, because I'm not going to read the definition, right? Or just let us quickly read it also, because it will help you to understand. So if V is a vertex in T, where T represents the tree other than the root, the parent of V is a unique vertex U such that there is a directed edge from U to V, right? So when we are drawing the tree, we are not drawing the arrows, but we are considering that edges are directed away, right? What is the meaning of child? So if U is the parent of V, then V is called the child of U. Very obvious. Vertices with the same parent are called sibling. So the terminology are very natural, right? Ancestors. So the ancestor of a vertex other than the root are the vertices in the path from the root to this vertex, excluding the vertex itself and including the root, right? So I hope you understand what do you mean by ancestors, like those which are coming before you in the family tree, right? Descendant, so the descendant of a vertex V are those vertices that have V as their ancestor. And then there is a term known as leaf. So a vertex of a rooted tree is called a leaf if it has no children. And internal vertices that have children are called internal vertices. The root is an internal vertex unless it is the only vertex in the graph. In that case, it is a leaf. It means what? That if I say that this is a graph, then since it is the only vertex in the graph, in this case we will call it a leaf. But suppose we have a rooted tree like this, right? So in this case, this will be internal vertex and these two will be the leaves. So let us understand this in detail through this example, right? So and before I take this example, this is another term that we use, subtree. So if A is a vertex in a tree, the subtree with A as its root is the subgraph of tree consisting of A and its descendant and all edges incident to these descendants. So everything that I just talked about, I will be taking two examples so that you are absolutely clear about that. So here is an example, and this I will be explaining slowly. I hope you already have noted down the definition from the previous slide. In the rooted tree T, so here T is the rooted tree and A is considered as the root. Find the parent of C. So first question is find the parent of C. So here we have C. So what is the parent of C? Parent of C is B, right? So the first question is what is the parent of C? So parent of C is equal to B. Next is the children of G. So children of G. So children of G are H, I and J. So I write H, I and J. I think you can just look at this tree and decide what is the term that they are asking, right? Next thing they are asking, what are the siblings of H? So these are all terms in English language as well. So what are the siblings of H? Where is H? H is this vertex, so their siblings are I and J. What do you mean by sibling? Because H, I and J are having their parent as G, so they are the children of the same parent, so that is why they are sibling. And all ancestors of E. So what are the ancestors of E? So where is the vertex E? E is this vertex, right? I am calling this vertex E. So ancestors of E are C, B and A. So C, B and A are the ancestors. Now the next question they are asking, all descendants of B. So all descendants of B. Those who do not know English or possibly might have studied in Hindi medium, can you put in the comment box that what is the meaning of these terms in Hindi, right? So the descendants of B. So here, where is B? Yeah, this is the B. So the descendants of B are C, D and E. Okay, so I write C, D and E. All internal vertices. So next I am going to find all internal vertices. So I removed all the already inked things, and so that it is a smooth picture. So first question they are asking, all internal vertices. So internal vertices means that it should have some vertex which can be considered as its children. So A is an internal vertex, right? Because it has B, F and G as their children. B is also an internal vertex because C is its child. F is not an internal vertex because now I am crossing those vertices which are not internal vertices, so that when we are talking about leaves we can just directly see. So A is the internal vertex, B is the internal vertex, G is also an internal vertex, H is so let us look at this. So C is also an internal vertex, right? So I am calling B, C, G. What about H? H is also an internal vertex. Let me write H. This is not an internal vertex because it has no children, I. And then J is also an internal vertex, so I write J here. Is there any other internal vertex? No, I guess no. So we have how many internal vertices? 6. A, B, G, C, H, J, right? Now what are the leaves here? So F is the first leaf. We can write F because, and D is also the leaf, so I am writing D. E is also the leaf, so I am writing E. Then K, then I which is already there, and then L and M. So L and M. I hope we have taken care of all the leaves. So let us look at this again. F is a leaf at this label, and at this label I is the leaf, so I already have written I. D and E are the leaves which I already have wrote, and then K, L and M. So K, L and M, these are the leaves. So I hope you have understood the terms like the previous slide was defining. What is parent? So parent means that someone who is just above you, right? If V is a vertex in T other than the root, then parent of V is the unique vertex U such that there is a directed edge from U to V, right? Child, so you understand. Sibling, you understand. Ancestor, you understand. Descendant, leaf and internal vertex, right? So all these terms are clear to you. So I hope you understood this. But before I go to the next problem, there is another part of this, that what is the subtree rooted at G. So subtree rooted at G will be this part. So I just have to take this part, and this is a subtree which is rooted at G. So what we can do, I leave this for you. You draw this G vertex here and then draw these components. So this will be a subtree that will be rooted at G. So basically it is a subgraph of the graph where I take this G and all its what you call descendant and ignore other vertices in the other side. Okay, so now let us move to the next problem of this kind to be clear about all the terms that we just learned. So the first part is which vertex is root. Let me write the answer here. So the first part A, the root is A, right? This vertex is the root. Second part, which vertices are internal vertices. So I'm writing the internal vertex A, B, C, D, F, H, J, then Q and T. So let us write A, B, C, D, F, H, J, Q and T. C part, which vertices are leaves. So E, you can see that E has no children, so E is the leaf. G, then I, K, L, M and N, L, M and N, O, P, R, S and U. So these vertices are leaves. D, which vertex are children of J? So children of J are, where is J? This. So children of J are Q and R. So Q and R are children of J. E, which vertex is the parent of H? Where is H? So this is H. So the parent of H is C. Now the F part, which vertices are sibling of O? So sibling of O is P, because O and P both have the same parent, that is H. Now G part, which vertices are ancestors of M? So M is here. Ancestors of M are F, B and A. So F, B and A. And finally the H part, which vertices are descendants of B? So E, F, L, M and N. So E, F, L, M and N. So I hope you are clear about this, because this is a very easy kind of question, and sometimes they ask in the exam that they will give you a tree and may ask you all these related questions. Okay. Now let us talk about m-ary tree. So a rooted tree is called an m-ary tree if every internal vertex has no more than m children. No more than means maximum it can have m children. And the tree is called full m-ary tree if every internal vertex has exactly m children. An m-ary tree with m is equal to 2 is called a binary tree. Means if there are two internal vertices or two children for every vertex, then it will be called a binary tree. Now here are some of the examples given, and we have to decide that which of them are full m-ary tree. So if you look at this example, and here there may be a conflict in the notation. Some authors do not call full m-ary, right? They just talk about m-ary tree, right? So we are sticking to the same notation as the Rosen book is following. So to avoid any confusion, you should be sticking to just one notation. Now if I talk about T1, T1 is an internal vertex and it has two children, this and this. This is also an internal vertex. This also has two children. So every internal vertex has two children here. So this is a full binary tree because there are two children. So this will be full binary tree. If I talk about this tree here, this is an internal vertex and this internal vertex has 1, 2, 3 children. This is also an internal vertex. So this also has 3 children. This is also an internal vertex, so this also has 3 children. This is also an internal vertex, so this is also having 3 children. So this is an example of full 3-ary tree. Full 3-ary tree. If I look at this example, this is an internal vertex and it has 1, 2, 3, 4, 5 children. This is an internal vertex, it has 1, 2, 3, 4, 5 children. This is an internal vertex, it has 1, 2, 3, 4, 5 children. So this is an example of full 5-ary tree. right? Here it is FULL, full fibery tree. Now if I look at this example, this is an internal vertex, but it has two children, this and this. And this is an internal vertex, but it has three children, right? So this is not a full m-ary tree for any value of m, because this vertex has two internal vertex. So this internal vertex has two children, this internal vertex has three children, this internal vertex has three children, this internal vertex has two children. So there are four internal vertices, out of which two of them have two children and two of them have three children. So it means that this is not a full m-ary tree for any value of m. Okay. Now next thing that we are going to talk about is ordered rooted tree, and it is not very difficult to understand. So just quickly go through it. An ordered rooted tree is a rooted tree where the children of each internal vertex are ordered. Ordered rooted trees are drawn so that the children of each internal vertex are shown in order from left to right. Okay. In an ordered binary tree, usually just called a binary tree, if an internal vertex has two children, the first child is called the left child and the second child is called the right child. The tree rooted at the left child of a vertex is called left subtree of this vertex, and the tree rooted at the right child of a vertex is called right subtree of the vertex. I hope it is clear. So if you look at this example to understand what they are asking, what are the left and right children of D in the binary tree shown below in the figure? So they are asking what are the left and right children of D. So where is D here? So clearly you can see that this D vertex, so F is the left child. This is the left child, right? And G here is the right child, right child. Okay. And what are the left and right subtree of C? So if I look at this vertex, here we have the vertex C. So left subtree is a subtree which has H as its root and J as its another vertex, right? So this is the left subtree which I have just drawn. And what is the right subtree of C? So right subtree of C has I as its root and then K as one of its child and then L and M. So this is the right subtree of the vertex C and this is the left subtree. So this is left subtree and this is right subtree. I hope you are getting clear or like you are getting the points that I am discussing, because this is the first video related to trees. So there are a lot of basic terminology that you are coming across, right? Now this is very important because questions may be asked from this topic, properties of tree. So the first property of a tree, and it is very, very obvious that a tree with n vertices has n-1 edge. And I am going back to the very first slide to show you that. So if you look at this example here, this how many vertices are there? 1, 2, 3, 4, 5, 6. How many edges it should have? It should have 6 minus 1, that is 5 edges. You can count 1, 2, 3, 4, 5. If you look at this, how many vertices are there? 1, 2, 3, 4, 5. How many edges it should have? It should have, or 6 vertices. I count it again, 1, 2, 3, 4, 5, 6. So how many edges it should have? It should have 5 edges. So there are 6 vertices, so 5 edges, 1, 2, 3, 4 and 5, right? So this is a very important property of the tree, that if there are n vertices, then it will have n-1 edges. Now there is a theorem, and this is also important, that a full m-ary tree, I am talking about full m-ary tree with I internal vertices contains m into I plus 1 vertices in total. For example, suppose I think I can take this example which I have shown you in the page here. So just give me a moment. So I removed all the earlier drawing and let us understand this. So the first result, they are saying that if a tree has I internal vertices, this is what they are saying, that if a tree has I internal vertices, then total number of vertices will be m into I plus 1 if I am talking about a full m-ary tree, right? So this was one example which I took, and this was a full binary tree, right? So in this full binary tree, how many internal vertices are there? So 1, 2, so and 3. So the internal vertices I is equal to 3, and it is full binary tree, so m is equal to 2, because binary tree, when m is 2 we call it binary, otherwise we call it m-ary. So m is equal to 2. So how many total number of vertices should be there? So total number of vertices n should be m into I plus 1. So m is 2, I is 3 plus 1, so it should have total 7 vertices. So you can count it: 1, 2, 3, 4, 5, 6, 7. If you take this example, it was a full 3-ary tree, right? So what is m? M is 3. And what is I? How many internal vertices are there? This is one internal vertex, this is second, this is third, and this is fourth. So total internal vertices are 4. So total number of vertices n will be 3 into 4, m into I plus 1, that is equal to 13. So you can count it: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So this is the first result, that a full m-ary tree with I internal vertices contains n is equal to m into I plus 1 vertices, and we will be using this result to solve problems. Then another theorem is that a full m-ary tree with n vertices has I is equal to n minus 1 by m internal vertices, and L is equal to this many leaves. So this is a very obvious thing, that because total number of vertices are m into I plus 1, so what is I? I is equal to n minus 1 by m. So the number of internal vertices is given by n minus 1 by m, where n is the total number of vertices. And how many leaves are there? So how will you count the leaves? Total number of vertices are n, and total number of internal vertices are this. So leaves are what? Leaves are total number of vertices n minus the total number of internal vertices. So n minus 1 by m. So if you simplify this, it will be m into n minus n plus 1 by m. So which can be written as m minus 1 into n plus 1 by m. So that is what they are saying, that m minus 1 into n plus 1 by m leaves. If you remember this result, then of course you can find out this result. So there are two more results here. So first is a full m-ary tree with I internal vertices has this many vertices and this many leaves. So what they are saying, the second part here, that it is given that if there is a full m-ary tree and it has I internal vertices, then it will have total m into I plus 1 vertices, which we already discussed, and the total number of leaves will be m minus 1 into I plus 1. So how will you count the total number of leaves? So the total number of leaves will be total I internal vertices are there, so n minus I. So n minus I is what? N is total m into I plus 1 and minus I. So I is the internal vertices, so the number of leaves will be m minus 1, I take these two terms, into I plus 1. So these many leaves will be there. And the third part is that a full m-ary tree with L leaves and has n vertices, then the internal vertices will be I is equal to this. So if you look at the third part of the statement, they are saying that we have a full m-ary tree, and leaves are, how many leaves are there? It has total L leaves, and total number of vertices are n is equal to m into L minus 1 by m minus 1. So these many total number of vertices are there. So how many internal vertices will be there? Internal vertices will be total number of vertices, that is m into L minus 1 by m minus 1 and minus total L leaves. So if you simplify this expression, you will get the internal vertices as this. So you should not get confused with these results. The only result which is the fundamental one here, that if there are I internal vertices, then total number of vertices will be this, and if the total number of vertices are this, if I subtract the internal vertices from this, I will get the number of leaves. Okay, now just to understand it better, let us quickly look at this example. That suppose that someone starts a chain letter and each person who receives the letter is asked to send it to 4 other people. Some people do this, but others do not send any letter. How many people have seen the letter including the first person if no one receives more than 1 letter? This is important. And if the chain letter ends after there have been 100 people who have read it but did not send it out, how many people sent out the letters? This kind of things actually nowadays is happening through WhatsApp messages, right? कि आपको एक मैसेज आ गया, अब इसको 9 लोगों को फॉरवर्ड करें तो माता रानी की कृपा होगी. I mean, earlier the WhatsApp message was not there, so they used to send the letters. Anyway, so the point here is that the chain letter can be represented using a 4-ary tree. So there are 2 kind of people. The one who follow this suggestion that you have to send it to the next 4 people, and some are like, they know that this is something that we should do, so they stop it, right? So those who stop it and those who do not send any letter, those who do not follow this instruction, they becomes the leaves. I hope you are getting it. And those who are sending it will be basically the internal vertex. I repeat my argument. If you have received a letter and you have sent it to the 4 other people, then in that case you are an internal vertex, and those 4 people, now there are 2 possibilities. Some of them may continue this chain. So if suppose the 4 people are A, B, C, D, A received the letter and he also sent it to the 4 other people, then A will be internal vertex. But suppose B, C, D are smart, they did not forward this, so they will be leaves. Okay, so I think this much is clear to you. Now it is given that the 100 people, like you read this line again, if no one receives more than 1 letter, and if the chain letter ends after there have been 100 people who read it but did not send it out, means these are 100 leaves. So how many people sent out the letter? Here it is a m-ary tree, so m is equal to 4 because every person is expected to send it to the 4 people. So what we know? We know number of leaves, we know number of m value, that is equal to 4. So what we have to find? We have to find n, that is the total number of vertices. So what we are going to do? We are going to use this result. That which result? That we have a full m-ary tree, so we know that m is equal to 4, and we also know that there are L leaves. So how many in total number of vertices will be there? Total number of vertices will be n, which is m into L minus 1 by m minus 1. So we are going to use this formula here. So the total number of what you call total number of vertices will be, let me write it again, it will be ml minus 1 by m minus 1. So ml m into L minus 1 by m minus 1. This is the formula. Which formula I used? I repeat it to avoid any confusion. The tree structure that we are considering is a 4-ary tree because everyone is expected to send the letter to the next 4 people, and in the end 100 people received the letter but did not continue the chain, so these are the leaves. So if we know that if there is a full 4-ary tree and the total number of leaves are 100, then the total number of vertices will be given by this formula. So m is 4, L is 100 minus 1 divided by m minus 1, so that is 4 minus 1. So how much is that? 400 minus 1, so 399 by 3 is equal to 133. So the total number of people who actually have seen the letter is 133. And how many people sent out the letter? So out of 133, out of 133, 100 are leaves. So those who sent out a letter are internal vertices. So the internal vertices I is equal to total number of vertices 133 minus leaves, that is equal to 33, right? So this kind of question may be asked, so you need to remember the result there. Now next thing that we are going to talk about, that label. So the label of a vertex V in a rooted tree is the length of the unique path from the root to this vertex. The label of root is defined to be 0. Now here also there are some conflict, because some authors considered the root at the 1 level, level 1, but here we are considering the root at the 0 level. So we are going to follow this notation, and so the label of the root is defined to be 0. The height of a rooted tree is the maximum of the labels of the vertices. In other words, the height of a rooted tree is the length of the longest path from the root to any vertex. So first let us look at this tree and assign the labels to it. So this is at 0 level. These 3 vertices are at label 1, because if you move from A to B, you have to cover one edge, means the length of this path is 1. And if you look at these vertices are at label 2. Why label 2? Because if you move from A to any of these 2 vertices, 4 vertices actually, so you have to cover, or you have to travel through 2 edges. So suppose I move from A to F, so A to B 1 and then B to F 2, A to E, so A to B, and so you can see that it is all these 4 vertices are at label 2. And obviously these vertices are at label 3, right? And there is a vertex H which is at label 4. Yes, because you have to reach H, you have to suppose start at A, so A to B 1, B to F 2, F to G 3, and G to H 4. So this is at label 4. Okay, and what is the height of this tree that they have asked us? So if I ask you what is the height of the tree, so height of the tree is equal to 4 here, because 4 is the highest label. So this is what the height is. That in other words, that height of a tree is the length of the longest path. So the longest path is of length 4, or you can look at this also, that height of a rooted tree is the maximum of the label. So the maximum label of the vertices that I have assigned is 4. So height of this tree is 4. Now another term is a rooted tree, a rooted m-ary tree of height h is balanced if all leaves are at label h or h minus 1, right? So first of all, if I ask you, is this a balanced tree? So the answer is no, this is not a balanced tree. Why? Because you see that we have a leaf which is at label 1, we have a leaf which is at label 2, we have leaves at label 3, we have leaves at label 4. So that is why it is not a balanced tree. A tree is balanced only when all its leaves are either at label h or h minus 1. So to understand this, let us take this example. So what is the label of this? Label of this is 0. What is the label of this? 1. What is the label of this? 2. All these vertices are at label 2. Label this is 3, 3, 3, 3, 3, 3, 3. And label of these vertices are 4, 4, 4, 4, 4, 4. So you can clearly see that what are the leaves here? This vertex is the leaf, 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 this is not the leaf, and all these are the leaves, right? So the leaves are occurring either at label 3 or label 4, and as per the definition, if the leaves occur at either label h or h minus 1, so the tree is said to be balanced. So this tree is a balanced tree. What about this? Label is 0, label is 1. These are internal vertices. Here the label is 2, this is 2, 2. Here this is 3, 3, 3, 3, 4, 4. So clearly it is not balanced. That why it is not balanced, I don't think I need to explain, because we have leaves at label 2 also, label 3 also, label 4 also. It can be balanced only when the leaves are at level h or h minus 1. What is the height of this tree if I ask you? Height is 4. What is the height of this tree? Height of this tree was also 4. Now let us take this example. Label 0, label 1, 1, 1, 2, 2, 2, 2, 2, 2, and all these are at label 3. Now if you look at this, what is the height of this tree? The height of this tree is 3, and if you look at the leaves, these two are internal vertices. This is also internal vertex. This is internal. This is internal, 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 internal. So all the leaves are at label 3. So this is also a balanced tree, because the labels of the leaves either should be h or h minus 1. In this case, every leaf is at label 3. So this is a balanced tree. Okay. So we have two standard results. The first one is that there are at most m to the power h leaves in an m-ary tree of height h. And here I am talking about an m-ary tree. I am not talking about full m-ary tree. So that should be clear. And based on this, we can prove this result as well, that if an m-ary tree of height h has l leaves, then h will be greater than or equal to log of l to the base m. And here we are taking the ceiling function, which is also known as the least integer function. So basically, whatever value I will get, I will take it integral value, which is greater than this, but out of all the integers value which are greater than log of l to the base m, we are going to consider the least of it. So these two are results. Sometimes they may ask this as a multiple choice question. So you should keep in mind. In case if you are interested, you can also look for its proof, right? But here I am avoiding the detailed proof. So I think this was all about this in this video. Here in this video, I have introduced you with the basic terminologies of tree. So in the coming videos, we are going into the further detail of it, right? So I hope you are enjoying the videos that I am uploading. And in case if you are enjoying and finding it useful, you should certainly share it with all other students, and you should like the video as well. So that's all from my side. Thanks for watching. Have a great day.